Hello everyone. I am Gr3 pursuing post-graduation in construction engineering and management from CEPT University. My roll number is PCM25125 and I'll be presenting about the project Integrated Sports Complex during the construction and execution phase, which was done during our Studio 2 CM4003 Construction Project Execution Monitoring and Control. Now, talking about the project. The project selected for the study is an integrated sports complex developed as a dedicated performance center for para athletes with infrastructure designed for accessibility and inclusive sport activity. It was India's first state of the art facility exclusively for the para athletes. The project consists of indoor sports courts, swimming pool, hostel facilities, dining areas, science lab, terrace gardens, and athlete sports spaces integrated with single campus. The total build-up area of the project is 24,290 square meter with an estimated project cost of 364 crores and construction cost of 253 crores, making it a large-scale institutional and sports infrastructure development. The project includes facilities for multiple adaptive and inclusive sports such as basketball, badminton, sitting volleyball, goalball, and para dance sport. The study mainly focused on construction execution aspects, including the site establishment planning, temporary utility planning, equipment planning, productivity analysis, sustainability measures, labor welfare, and ESG compliance during the construction phase. Now, talking a bit about the site context, as you can see, the site is in near proximity with the railway line and has two entry points to the site. One is officially for the existing office, and the second was built during the construction phase of the project just for the heavy movement of the vehicles. Now, talking about the site context, layout, and establishment planning. A detailed site establishment planning was carried out to ensure efficient workflow, uninterrupted construction activities, and safe movement of labors, materials, and heavy vehicles. The site layout was divided into different functional zones, including labor colony, batching plant, steel yard, quality lab, material storage area, weigh bridge, site office, and equipment movement areas. Separate entries was given out, while the first entry was for the heavy movement of heavy vehicular entry, while the office entry was given separately to reduce congestion and avoid interference between workers and machinery operations. Then temporary infrastructure such as site office, labor accommodation, utility lines, barricading systems, drainage arrangements, and storage areas were established before starting major construction activities. Hard barricading was proposed near permanent high-risk areas and heavy equipment zone, such as near the labor colony, near the quality lab, and protecting from the existing buildings from the construction zones. While soft barricading was used around temporary work areas, like in case of excavation areas, to improve worker safety and site segregation. The planning inference showed that the proper zoning and circulation planning reduced material handling delays and improved accessibility. While the site office and labor colony were zoned away from the construction area and for faster evacuation as well, while the steel yard, the batching plant, the quality lab, and the weighbridge were zoned in a circular pattern for easy accessibility. And as you can see in the side, there are two main tower cranes and one mobile crane for material handling in the project, and the tower crane is in 50-meter proximity from the steel yard. And various equipments are used in the project for using on-site for material handling, excavation, and concreting, which will be later on discussed in detail. So this table shows the different equipments has been used. Now moving on, let's understand about the water demand assessment and distribution network analysis. The water demand calculations was carried out considering construction activities such as RCC curing, plastering, batching plant operations, dust suppressions, equipment washing, labor colony usage, and drinking water requirements. The study identified that the major water consumption on site comes from the known potable activities such as curing and construction operations, accounting for 92.79 kiloliter per day, while drinking water demand was only 4.67 kiloliters per day. A borewell with a depth of 550 feet was proposed as a primary water source after obtaining necessary approvals from authority. Considering the groundwater table and site conditions, as in present scenario, the groundwater table is below 30 meter. The water supply system included underground storage tank of 25,000 liters capacity and overhead tanks, curing tanks, distribution pipelines, outlet valves, and extension line planned across the site. Then drinking water for workers and staff was supplemented through external tanker supply and packaged water cans to ensure safe potable water availability. In the site, two water tanks of 6,000 liters were provided near the labor colony, while one underground water tank of 25,000 liters was constructed near the batching plant for its use, and a 500-liter capacity water tank was constructed near the site office for the site office purpose. And water outlet valve was kept in around the site to provide water extension lines. The analysis concluded that proper storage and distribution planning is essential to avoid interruptions in curing and batching operation during peak construction periods, while also ensuring labor welfare requirements are met efficiently. Now let's understand about the electricity demand analysis. The electrical load analysis was carried out considering all construction machinery, batching plant operations, pumping system, office, labor colony requirements, temporary lighting, and utility services. The total site connected load was calculated as 682.8 kilowatt with the highest power demand generated from construction equipment and temporary construction utilities. The temporary electrical infrastructure include HT connection, DG sets, main distribution board, sub-distribution board, underground cabling system, earthing arrangement, and protective systems such as MCCB, MCB, and RCCB. Different electrical load distribution scenarios was analyzed to compare operational costs, comparing only torrent, the load taken from only torrent and the load distributed between torrent power and DG power to compare operational cost, DG dependency, and power efficiency between grid supported and DG dominant system. So such that the grid supported system is more suitable in this process. The study show that integrating DG grid supply and optimized load reduces diesel dependency, improves reliability, and minimizes long-term operational cost. Now, looking onto the electrical plan shown in the slide, the main distribution board is situated near the site office entry, and then it is connected to the distribution board, which is situated in the center of the site, which connects to the sub distribution board, which will connect to the DG sets and other important electrical demands in the site. Proper electrical planning also ensured safe, temporary power distribution, reduced risk related to electrical faults, overloads, and unsafe temporary wiring on site. Now we'll be studying more about the equipment planning done in site. So there are different types of equipments for lifting, reinforcement, concreting, and excavation. First, we'll be looking onto the lifting and reinforcement equipments. Lifting equipment planning was carried out based on building height, lifting radius, material handling demand, equipment capacity, and construction sequence requirements. Different lifting equipment such as tower cranes, hydra crane, tilt crane, mobile tower cranes, material hose, and passenger lift were deployed for different construction zones and material handling operation. Two tower cranes were strategically positioned to improve vertical transportation efficiency and minimize delays during material transfer between slabs and construction zones. The lifting capacities, jib lengths, working hours, and operational range of cranes were analyzed to ensure safe and uninterrupted handling of reinforcement, shuttering, concrete, and masonry material. In this case, the jib length of the tower crane is around 50 meter. So the steel yard is also zoned near the 50 meter for proper material handling of steel yard. The reinforcement planning was carried out for a total peak steel quantity of 4,047.31 metric ton with a peak reinforcement demand of 3.5 metric ton per day during RCC activities. Bar bending, cutting, threading machines were selected based on reinforcement diameter, processing speed, productivity requirements to improve reinforcement handling and reduce labor dependency. Now we'll be looking onto the equipments in concreting. Concreting equipment planning was carried out using project schedule analysis and peak demand calculation obtained from MSP scheduling data. The peak demand concrete demand during the raft foundation work was identified as 35.78 cubic meter per hour, requiring continuous and uninterrupted concrete supply to avoid cold joints and delays. A 60 cubic meter per hour batching plan was selected because it satisfied both average and peak demand concrete demand efficiently while avoiding underutilization associated with the larger capacity plants such as a 90 cubic meter per hour system. Transit mixtures, boom places, and concrete line pumps were selected based on the pump output, travel distance, building height, vertical reach, and cycle time requirements. As in this case, the cycle time of the transit mixture to the batching plant is around 28 minutes, and the boom placer with 35.6-meter vertical reach and 31.7-meter horizontal reach was selected to satisfy the building height requirement of 25.8 meter. A cost comparison between hiring and owning equipment shown that the owning concrete equipment is more economical than long-term duration project due to reduced cumulative higher cost during the project duration, and we can almost reduce 18.54% of the cost by owning the equipments. The analysis concluded that accurate productivity calculations and equipment optimizations are critical to achieving uninterrupted concreting operations and reducing operational delays. Now let's understand about the equipment in excavation. Excavation planning was carried out for raft foundation and isolated footing, and the basement excavation works reaching a depth between 7 to 8 meters in hard, silty clay soil conditions. Equipment such as excavators, loaders, tippers, compactors, backhoes, tractors, diaphragm wall rigs were selected based on excavation quantity, soil conditions, and required productivity. Two excavation scenarios were analyzed to compare productivity, working hours, project duration, and equipment deployment efficiency. Scenario 1 uses fewer excavators and trucks, resulting in a 76 days of excavation work, while Scenario 2 increased the equipment's quantity and reduced the number of days from 76 to 26. The analysis showed that increasing excavation equipment improved the productivity from 154 to 437 and reduced the project duration by 50 days, improving the total project duration. The DG optimization analysis was also showed that reducing DG sets from 5 to 3 lowered the total connecting load by 83.05 kilowatt and significantly reduced the fuel consumption and operational cost in this project. The study inferred that the equipment productivity analysis and temporary power optimization directly influence project timeline, cost saving, and operational efficiency. Now we'll be talking about sustainability analysis in the project and how sustainability can be introduced in the construction phase of the project, which can overall impact the project. Sustainability analysis focus on reducing environmental factors through circular economic principles, waste reduction strategies, energy optimization, and sustainable material selection. Construction waste analysis identified steel scrap, AAC block waste, concrete waste, and shuttering waste as major waste stream generated during the construction activity. Circular recovery strategies show that nearly 80% of the steel scrap can be recovered and reused, while approximately 50% of the AAC blocks can be reused, resulting in significant material and cost savings. Green AAC blocks were combined with standard AAC blocks and showed nearly 60% of lower embodied carbon emissions due to higher fly ash and recycled content. The energy consumption analysis combined DG heavy systems with grid support systems and showed substantial reduction in diesel consumption and carbon emissions during HT grid integration. The total CO2 per day is reduced from 2.4 tons to 1.91 tons. The project also adopted carbon reduction strategies such as reducing idle running of equipment such as tower cranes, optimizing tower crane usage, then integrating LED lights to halogen to LED, and then improving energy efficient operations. The analysis concluded that sustainable material selection and energy optimization significantly reduce the environmental impact in the project. Now let's talk about the water consumption and cost associated with sustainability measures. The water sustainability measures included curing compounds, wastewater recycling, grey water treatment, and reuse system aimed in reducing freshwater dependency during construction phase. At 25 kiloliter per day MBBR treatment system was proposed to treat wastewater generated from labor colonies and site operations for reuse in flushing and non-potable application. The analysis showed that the wastewater treatment system can reduce freshwater demand by nearly 20 kiloliter per day while minimizing groundwater extraction from the borewell system. The labor welfare and ESG analysis covered PPE usage, sanitation facilities and accommodation conditions, drinking water supply, and worker welfare preventions. The monitoring systems such as water meters, energy meters, and noise meters were proposed to track resource consumption and ensure compliance with the environmental and safety regulations. The study identified gaps between what is the current SDG remind and what is happening in the current site condition, which is not meeting the sustainability targets. The analysis concluded that integrating labor welfare governance system and environmental monitoring significantly improves sustainability measures, worker safety, and compliance during construction activity. Now, to conclude, this study demonstrated that detailed site establishment planning improve workflow between labor colony, batching plants, steel yard, QC lab, site office, and utility networks for smooth workflow. Then use of barricading and temporary surface. In equipment planning based on productivity analysis, peak demand, lifting capacity, and project duration was done to ensure efficient construction execution. An excavation study comparing between two scenarios was done to reduce the duration from 76 days to 26 days, saving literally 50 days. And the selection of batching plant of proper 60 cubic meter per hour rather than 90 to avoid underutilization, and calculating the number of transit mixtures required in the site based on the cycle time. And at last, the sustainability analysis, which focused on reducing environmental impact during dust control, waste management, water conservation, and energy efficient practices. So, this is about SEM2 project integrated sports complex. Thank you.